Okay, so hello, welcome back. So my name is Wei. I'm from the AMAC EuCNC. I will be talking about how to use Open Wi-Fi on one of the testbeds that's Fed4FIRE compliant. Let me try to enable presentation. So, okay. So in this part, we will talk first about introduction about what is Open Wi-Fi and then show how to use it in the validity testbed, which is a Fed4FIRE compliant testbed. About the introduction, so it will be very simple and straightforward. First, what is Open Wi-Fi, and then I will try to convince you why you should use it. And finally, we come to the part to talk about how to use it in the testbed. For what is Open Wi-Fi? So the short answer is that it's an open source IEEE 802.11 compliant Wi-Fi baseband chip. It's implemented on the FPGA, meaning that the part is realized on programmable hardware. If you simply Google Open Wi-Fi, you should find it on GitHub. So you should find this link very easily. The picture below gives you a bit more information about what is Open Wi-Fi. So the idea is not to discuss everything that is on the picture. However, I would like to stress that only the blocks that's highlighted in the yellow are part of the Open Wi-Fi. So we actually utilize a lot of existing tools, like from the user space applications and also the kernel modules to form a complete full stack communication that's compliant to the Wi-Fi standard. Among the three parts that's highlighted in yellow, so we have a simple user space program that can be used to talk to the driver. The driver talks to the hardware that's on the FPGA. So this is the three components that forms the current Open Wi-Fi system. So let me go to the next question. The next question is that, is Open Wi-Fi better than a commercial Wi-Fi chip? The answer is yes and no. Yes means in some aspects it is better. No means in some others, actually many others, it's not. So you might start to wonder if it could have been a worse device, then why should I use it? So like I said, there are some aspects that Open Wi-Fi performs better because of the special unique feature that actually the Linux and the Wi-Fi interface are situated on the same chip. They call it a system on chip, so SoC. So this makes the interaction between the kernel and the hardware much faster. That's why if you would perform a ping, you will see that the latency is lower than average commercial chip. So a bit more complete overview on the comparison between the Open Wi-Fi and the commercial Wi-Fi chip. In terms of the connection between the network interface card and the processor, for this aspect, we can see that Open Wi-Fi has a dedicated high-speed on-chip bus. This offers a ping round trip time of around 300 microseconds, whereas on the other hand, on the COTS device, you have usually the USB or the PCI Express based interface. So this gives on average a latency round trip time of about 1 millisecond. Another aspect is whether you can offload some processing tasks between software and hardware. So for Open Wi-Fi, this is no problem because we have the programmable hardware device. So for instance, we have realized some crucial features that's required by the time-sensitive network. So in PSN, usually you need some synchronization between devices, and therefore you need to timestamp when the packet leaves the device or when you receive a packet. So we could, for instance, offload this kind of critical tasks that requires a very accurate timestamping in the hardware. Well, there are other examples, but it's all application specific. So the point being that for Open Wi-Fi, we can easily distribute certain tasks from between hardware and software. Whereas for the commercial chip, this is not so flexible. However, they have some features that at this moment, Open Wi-Fi is not fully supporting or a bit lacking. So there were encryption, more advanced features, packet filtering. So they focus on more on the consumer market, whereas for Open Wi-Fi, you have the opportunity to customize it for some more professional network. So another aspect is the integration level. For the Open Wi-Fi, as it's a FPGA-based SoC chip, so you can put many of these functionalities on the same chip. Whereas for a commercial system, it's typical that you have multiple commercial chipsets that's distributed. Also regarding whether it can be upgraded in the field. So for Open Wi-Fi, because we use FPGA, so we can easily integrate new feature or bug fix or do optimization to the hardware. But this wouldn't be the case for the commercial chipset, because once the silicon is hardened, you can't easily program it anymore. So this slide gives you an overview of what has been improved in the past year in 2020. So of course, it's not ideal to read all this, but just to highlight a few. So we have some new features such as the channel estimation becomes more accurate. We have the low MAC being improved, more cost feature supported. Some bugs are being fixed, so it's more stable. So this gives an idea that what kind of improvement we have been incorporating in the past year. So how could Open Wi-Fi serve your products or research or applications? So the first thing is that you can hack the openness. Open Wi-Fi is released under the AGPL version 3 license. So you can use Open Wi-Fi to build your unique open product and ecosystem all for free. There's also secret competence. You have the early access to the advanced and unique features. And you can also even propose your own customization ideas and needs. So if you have any ideas regarding some usage of Open Wi-Fi, please feel free to come, and we are very happy to discuss with you. Since I'm still on a mission to convince you about why you should use Open Wi-Fi, so I have listed a few motivations below. The first thing would be that if you are curious how Wi-Fi works, then Open Wi-Fi would be the ideal knowledge base to learn how you could transfer information from your application to the antenna. So everything you need to know in the full stack communication is basically in the Open Wi-Fi repository. So it's a great place to learn. Another type of things that you can do is that if you have ideas to improve Wi-Fi or customize Wi-Fi for your scenario, but for some reason that the Wi-Fi driver is complicated, you don't know which part you need to modify, or if the Wi-Fi card has a full MAC, means including all the MAC layer, everything is hidden in the chip, you don't have access, then you cannot, of course, do any optimization or change anything. So the third possibility is maybe you want to modify some part of the chip, but it's not possible because the silicon is already hardened. And also it's possible you want to see how your new algorithm like antenna, RF, power amplifier, so on. If you have ideas to improve these parts, to observe your network performance. So all these things you can achieve in open Wi-Fi, but would have been hard if you use a commercial Wi-Fi chip. If you're still not convinced, we have some statistics that shows how others have been, how many others people already been using open Wi-Fi. So this part are a couple of universities that's already using open Wi-Fi for educational purposes or research purposes. There are also industrial companies. And on the GitHub, up to actually today, we have more than 2K stars, 300 forks, many watches, also many issues being resolved, and it's being ranked number 2 among the topics that's using the Verilog language. So Verilog is the language you use to implement hardware in the FPGA. So this gives you an idea that there are many universities, companies, and also individuals are using open Wi-Fi. So I hope you have a bit more confidence and interest also to try it. If you are still not convinced, I will show a video made by my colleague for the FOSDOM conference. So this is a fast video. Please don't blink because there are many information that flashes fast on the video. Let me try to start it. Before that, I will share the sound. Did I just share it? Okay, so let me try
to. We don't see the video. Yeah.
I remind you.
You don't see the video?
We still see your screen, your site. So maybe you only shared the PowerPoint.
Let me try to share it again. I shared my desktop. Okay. How about now?
Yeah, that's better.
Okay,
yeah.
Let me restart.
Yeah, that's good.
Sorry for the mistake.
I remind you, this is not a joke.
Okay, so that's everything about the video. I hope you are a bit more convinced and are ready to use Open-Wi-Fi. Let me go back to the presentation. So actually, I will stop this. Okay, continue. So let's come to the last part, which is about how to use. If you have a board that we support for Open-Wi-Fi, it's very simple. Then you just follow the GitHub README. So there's a quick start section. So basically it comes down to burning an image to the SD card, put it into the board and boot. So it's very straightforward. If you do not have a board, then you're very welcome to try it on the testbed. So this is what we are going to discuss. So in this part of the tutorial, I will first show you a web page. All the information, all the steps I will be taking is based on the web page. So all the information is there. After that, I will talk about where are these boards installed and which types are being installed. I will also show you some basic JFET information about reservation and experiment that's specific to the Open-Wi-Fi boards. After that, we will boot an SDR with the image and also do an experiment, which will use the Open-Wi-Fi to communicate with other Wi-Fi devices in the testbed. At the end, I will also mention some important aspects. So for the testbed webpage, if you go to the tutorial page of the YWT testbed, or in fact, you simply search Open-Wi-Fi and YWT, you should find this page quite easily. About the boards, so we have currently 3 types of SDR boards installed that you can reserve to run Open-Wi-Fi. The first type is the EuCNC SDR. It's basically 2 parts. It's one part is from the Xilinx evaluation kit, from the EuCNC evaluation kit, and another part is from analog devices. So this is the RF front-end board. So we have 3 of these types. We also have another type, which is called the ZCU102 Zinc SDR. So it looks like this. It's actually one of the most expensive SDR boards with support for Open-Wi-Fi. So it's from the ultra-scale Zinc family, means the FPGA is bigger. And also there are, I think, 4 cores in the ARM. So you can integrate more features into this board. Currently, there are 4 of these installed, but at this moment, they are all reserved for internal projects. However, we anticipate that they will be available also for the public in the near future. There are also 2 types of dead zinc SDR. So this is the cheapest SDR boards we support for Open-Wi-Fi. In this board, you can run it. It's with a smaller FPGA, and also the ARM has less cores. But it runs perfectly. So later on in the demo, I will be using one of these types. Okay, so these are all the boards that we have in the testbed. So where are the boards situated? If you would serve to this website, so this is the inventory website that all the reservations has to come from in the YWT testbed. So if you go to this website, you will see a view such as below. So this is basically a top bird view of not all the nodes, but some of the nodes in the testbed. So when I make these slides, I took a screenshot with some filters. So in this way, you can see that SDR boards that I have been showing before are actually the nodes that's been shown in the black circles. So like these ones. So it's also important to know what are the connections between the boards and the outside. So first of all, we have a power connection on the right side. So this is controlled by a power distribution unit. So it can be remotely controlled. Actually, it's you can reboot the board via the JFET application. You also have another two interfaces on the left side. So the first one is a UART. So this is connected to typically what I call a host node. It can be a DSS or APU, can also be a server. It's not so important, but so the UART and also the JTAG interfaces are actually two USB cables that's being plugged into a PC in the testbed. It's important you reserve this PC together with the SDR so that you can configure and boot the SDR. There's also a Ethernet interface. So this Ethernet is connected to a experiment switch in the testbed. So through the JFET application, you can basically configure, for instance, make a VLAN between some ports that connects this interface to another node that can be a host node or any other nodes in the testbed that you have defined into the JFET experiment. What I also want to say is in the testbed, there will also be a SD card plugged in into this slot. It's a little bit different than shown on the GitHub README page, where you would use the SD card to boot this board. So here, the SD card actually is only used for root file system. The booting files, such as the FPGA configuration, the Linux configuration, comes from the JTAG interface. So we especially made this design because otherwise we have an issue. If you would have some user that accidentally destroy this SD card, then other people wouldn't be able to use it, or some user might want to use a different Open-Wi-Fi version than another. So in this way, based on these reasons, we decide to use the JTAG interface to boot, so that every user, when you power the device on, it's a blank paper. You can download your own FPGA bitstream, your Linux kernel, so on and so forth. So every user comes with a fresh configuration, and nobody will. So there's less risk that you can have a board that's no longer bootable. So when you want to use the Open-Wi-Fi board in the testbed, you have to reserve and also define a JFET experiment. So the minimum you need to reserve is an Open-Wi-Fi board and a host node. So it's important that you also define a link between these two if you want to use Ethernet. So I typically put them into the same, the private 10.something network, so that you can bridge the Z board from the host node. You can, of course, define other addresses, but then you need to configure the board after once it's booted to make sure it's in the same subnet. You don't need to specify any image on the host node. You just need to define a link and then activate the experiment. So I will soon do a demo about how to use it. So the demo will come down to two parts. In the first part, I will boot the Open-Wi-Fi image. So I will go through all these steps. And then in the second part, we will use the Open-Wi-Fi to communicate with another Wi-Fi device. So, okay, now let's come to the demo part. So before I start with the JFET, I would like to show this web page. So this is the web page where we have all the nodes you can see in the ViaDuct testbed. So if you want to know where is the Open-Wi-Fi boards, you can simply type this. So this selects, filters out some other nodes. Otherwise, it's too many to see. So now you have only the Open-Wi-Fi boards left. So today I have actually a running reservation going on. So I will do a demonstration. So here I have reserved the Z-Sync SDR1, server 9, Zotac C7, and D4. So this comes to this node. This is what we are going to use. I will try to clear it so you also see the others. So for this SDR, I have the host node is server 9. I have also reserved some other nodes. So later on we can communicate with, for instance, this node via the Wi-Fi interface once it's set up. Then let's come to the web page. So this is the tutorial web page that shows you how to use Open Wi-Fi in the testbed. I will skip this part. So some gentleman's agreement. So although you have, each person can download configuration from the JTAG interface, but the SD card, the root file system is still shared. So it's good to have some common practice to not override other people's stuff. So I will start from the booting Linux part. So I already made a reservation, and I have also activated the experiment because otherwise it will take a while. So in this experiment, you see that we have the server 9, the Z board, and the link configured, and also 2 other nodes that has a commercial Wi-Fi interface that we'll be using later. So I will skip these 2 steps, but start from the 3rd step. So once the experiment is started, we should reboot the SDR by right-click on the node in JFET and then select reboot, then reboot OS. So now I will do this. So you see that now actually behind the scenes some scripts are running. So it's using the power distribution unit to power cycle this board. Maybe let me try to put it. Okay. So the next step is that I should log into the host node and establish a serial connection to the board. I should follow another tutorial for the serial setup. Afterwards, I should come back to this tutorial to continue. So I will open this link in a new tab. Okay, so this is the part I will be following. So let me try to first log into the host node, which is server 9. Okay, so I am into the node. Let's try to put it like this. So I will make this a little bit bigger. I hope it's visible. Okay, so I will try to run this command. And then, so since we already have Minicom, we don't need to install it again. But if it says no Minicom, then you should do this to install it first. So I should then select serial port setup, type enter. So I will select this. And I should type A to add the COM port. So since we're using the Z-Sync SDR, So we'll be using this COM port. After that, I should also type F to turn off the hardware flow control. So this is what I will do. So the flow control is now off. So if you're using this is 706 board, this is all you have to do. However, for the Z board, there is some additional steps. So we need to configure the modem and dialing options. Basically, what we'll do is I will first enter and go to that menu. So I select modem and dialing, and then I should set everything to nothing, starting from the option A to option I. So I will now starting to select A. You see there are some characters. I will delete everything and then type enter. So I will now repeat this for the rest of the menus. So of course, there are ways to save this configuration, but if it's the first time you have to do this. But afterwards, you can save it as default configuration. So I did everything. Let me just try. Okay, so now I will type enter. So after that, I should just exit. So this should be the end of the setting up serial connection part. So then we go back to the original tutorial. And since we are complete with step 4, we have opened the UART connection. Then we continue with step 5. So in this step, we should use a zip file. We should upload this file to the host node. So I will start downloading it. Apparently, I already had one. So let me just use this one. So I will use a JFET to transfer a file. So I will browse to the file location, which I have it on the desktop. So it's this file. So for the remote location, I will just choose camp. So now the JFET tool is uploading the zip file from my local PC to the server 9 in the testbed. After that's complete, I need to unzip it and go to this directory. So what I will do is I will open another terminal towards this server 9. So now I will see that the zip file is indeed where I specified in JFET. So I will now unzip it. So now I have this folder at my on the server. So after that, I should open terminal and set up some environment variables. So basically, in this step, we will be setting some environment variables up so that we can use this settings to download the FPGA bitstream and Linux configuration files. So let me try to do this. So this I will run this application from Xilinx. Maybe before that, I will also take a look at the content of this folder. So you can see that the folder contains a Tico script, and also some other folders. So for instance, in this zinc common folder, you will see there's a Linux image. So this is a kernel image that will be downloaded through the JFET interface to the board. There's also some files in this folder. You can see that there are 2 folders for each type of the board that we support. So for instance, for the Z board, you can see that this contains the FPGA bitstream, the device tree for the Linux, some first stage and second stage bootloaders. So these are all the files that will be used by this Tico script. So now I will try to run the Xilinx tool. Sometimes it's possible that after you run the Xilinx tool, you might run into some errors that the error will look like something like below. This, by my experience, is caused by some local environment set up in your terminal. So in that case, you should try this command. But most of the time, actually, there won't be any issue. So inside of this XSDB console, so you should first run this command so that the script knows that which board you are running. So this is what I will be doing. Yep. After that, I will run this Tico script. So you might also run into some errors, but basically it should be fine. So this script will be first downloading the FPGA bitstream. After that, the first stage bootloader, device tree, so on and so forth. So it's configuring the board as we discussed before. So now at this step, you can see that everything is downloaded. So now we can continue to follow the instructions such as here. So I will hide this terminal. So we need to run this command and then get ready to interrupt the auto boot process in the serial console, which is on the left side. Try to align the left with that. So now I have stopped the auto boot. At this moment, actually, the JTAG interface is no longer needed, so I will disconnect to avoid that it might interfere with the booting process. And then I will run this command so that the U-boot will finally launch Linux. So as you can see that at this moment, the board is booted. Okay, so now we have succeeded at to this part of the tutorial. So I will continue to the next part, which basically helps you to log into the board through the Ethernet interface. So right now we have the serial interface. I will take a look at the interfaces it has. So we have a Ethernet interface and also local loopback. However, in fact, at this moment, you can see there is no Wi-Fi interface on the board. This is normal because we didn't really load the driver yet. So the Linux has no information about the hardware that's running on the FPGA. So we also see that it has a IP address that's as specified. So let me try to show you the other terminal. I will exit XSDB console and also do if config here. So here we see that we also have an interface that's in the 10.something network as configured by the JFET2. So in fact, the JFET2 can only configure the interface on the host node and on the switch, on the VLAN switch. So this part, if you have specified another subnet, it's possible that you will see something else. In that case, you just have to manually adapt the IP address on the board. So in my case, I don't have any, I just have the default information that's correct. So I will go back to the tutorial and see that I can simply run this command to log into the board via Ethernet, and the password is also Openwifi. So okay, so now I'm also logged in from the Ethernet interface. So in the next step, we will start to load the drivers, and hopefully we will see the Wi-Fi interface on the board. So I need to download these files to continue. So I will start to copy link address. Since we have the Ethernet connection, I don't need the serial anymore. I will get out of minicom, and then I will get this file from the URL. So now we have this root file system.zip. I should copy it to the board. So right now it's on the server 9, it's not on the board. So I will try to unzip it. And I will also take a look at what is on the board. Okay, so it has already this folder, but I will copy it and give it another name. Wait. So this is actually why we need the Ethernet interface, because it's more convenient to transfer files from the host node. Otherwise, it would be difficult to do this step. So let's see. Yes, so the folder has been copied. I will now go to this. Okay. So so now we are at this step. So I need to copy modules and create a symbolic link. So this is because Openwifi relies on certain Linux kernel modules to do this full stack communication. So the driver needs to talk with some modules. We need to make sure that the kernel finds the correct module that's compatible to the kernels you have downloaded through the JFET. So this is done by first remove a symbolic link and then create one. So I can copy this command and then go back to this. So before I do that, I will take a look at this folder, the content of the folder. So there are two subfolders here. You have the ADI Linux module. So inside of this, you see that there are a couple of kernel modules here located. And then another folder here is the user space. So here we have the scripts and some tools that you can use with Openwifi. So first thing I will do is that I create a link so that the Linux kernel finds the modules in this folder. So this is done by this command. Okay. After that, I will run this command so that we insert the necessary kernel module that Openwifi driver will be interacting with. So first DEP not. So there will be some warning message, but this is just some user complaint. You don't have to mind this step. So what's important is that you can insert the next module. So after this step, you should see that these two modules are being inserted. And then I come to step 4. So in this step, I need to copy the driver files to the user space by go to this folder and execute this command. So I will go to this user space folder and then do this. So basically, you can take a look before. So there were some driver files in this folder. So this is actually a reason because there are sometimes different format of the kernel modules, like for 32 or for 64 bits. So this is why we do this step to copy, but of course it can easily automate this to simplify things. So after that, you see that some kernel modules are here. I also need to compile this strctl too, because sometimes you need to set some registers. So it's always handy to have it. So I will go to this folder and start compiling it and copy it to the folder above. So these are the source files. Okay. Now I copy this to the folder above. Now you can see that the strctl appears here. There are quite some scripts here, and some of them do cause this binary to do some settings. So something I usually do when I use the noding testbed is to set the antenna. So let me just show the content here. So for instance, in this script, you have some flexibility to select which antenna ports to use on the Openwifi interface. So you can, behind the scenes, the script is using this binary to set some registers. So this is why we need to do this step. So after that, I will be stopping the network manager. Sometimes this network manager interferes with the Openwifi. So at this moment, we will stop it so that we can use it the way we want. So finally, I came to the step to execute this script. So this actually will load the drivers. After this step, you should see the interface. So you'll see some errors. It's because the script first tries to remove the modules if it's already existing, and then insert it again. The errors actually says there's nothing inserted. So it happens when you first time load the driver, but it's not a serious error. So now, as you can see, we have created the interface SDR0. So this is the Openwifi interface. I will now bring it up and then try to use it to scan. So this command should give it doesn't return anything, means there's no SSID, or maybe some, okay. Sometimes it's a weak or just bad luck. So it does see some some SSID, so some access point have been set up in testbed. So for instance, in our case, it's a EDU row that's used by the university to provide Wi-Fi to the students. So it has this channel, this signal strength, some capabilities. So yeah, this means the interface is up and running, so everything is okay. So then I will go to the next part of the tutorial, which actually uses the Open-Wi-Fi interface to communicate with another node. So this is explained here. In this section, we will first set up the Open-Wi-Fi access point. So this is done by executing this script. So I will come back to the terminal. So if you take a look at this folder, you will see that there is a script called Boston. So I will take a look at the content of it. You'll see that basically it will repeat some of the steps we did before, like loading drivers, stopping the network manager. In addition to that, it will go a bit further. It will configure some IP address on the interface and start a DHCP server and start the host APD. So it's this command that will actually configure the Open Wi-Fi interface to behave as an access point. So I will just go ahead and run it. Okay, so it prints out a lot of stuff, but what's important is that at the end, you see that the access point is enabled. So now the AP should be running. We should then create a configuration file on a commercial Wi-Fi node. So I will go back to the JFET experiment. So I have reserved 2 of these regular Zotac nodes. So I will just log into one of these. Okay. So I'll also make it bigger. So you see that it has a VLAN interface. I will now try to scan the SSID. Sorry. I also need sudo because it's not root here. Okay, so apparently it scans a bit more SSID than the Open Wi-Fi interface, but I would like to see if the Open Wi-Fi is among one of the SSID that's being found by this node. There are many access points running apparently. Let me try to do it back. Okay, so actually there is a Open Wi-Fi access point being detected. However, I must have missed it when I screw up like this. Okay, so then in that case, we can continue to configure the client. So what I will do is I will create a configuration file. So in this file, I will tell the WPS applicant that the SSID is Open Wi-Fi, and we don't need any authentication here. So after the file is created, I will now run this command. So basically, it will tell the application to associate with Open Wi-Fi. So I will also show the terminal, which is here. Okay, so you see that it says connection to Open Wi-Fi. So this is the MAC address of the AP. So so on the AP side, you also see that it's reporting a device is connected. And then we should run this command so that the device gets, the interface gets an IP address from Open Wi-Fi access point. So if I would show the interface now, you'll see it has no IPv4 address. Okay. Okay, now it actually has one. I'll also show this part. So for the Open Wi-Fi, we also have an address in the 13.something subnet range. So this was configured by this FOSDOM script. So at this moment, actually it's ready. So we can now, for instance, do some ping from the commercial Wi-Fi nodes to the Open Wi-Fi. So I will now start pinging. So as you can see that we have a ping connection between the devices. So of course, yeah, we are actually already established the link, but it's always interesting to see some more configuration through the driver. So what I will do is I will now show the kernel log. You see that the kernel log already shows during booting time some configuration has been done, like for instance, for the host support, there's a contention window minimum maximum for each of these FPGA queues. If you want to see something more, then you would need to do some configuration on the driver. So for that, I will go to the Open Wi-Fi public repository. So for instance, I will Google Open Wi-Fi. So generally, it's the first hit. So in the repository, there are many documentations. You can find it here under the doc folder. So there are some application notes, but for today, I will just show, yeah, some debug methods, for instance. So go to this section. So here you basically see some command that uses the SDRCTL to enable some more printing. So for instance, if you run this, you would enable all kinds of printing on the transmission side. So I will do this. And then if I do the message again, I will see that there are some print out. So this is from the Open Wi-Fi TX. So Open Wi-Fi TX is actually a function name that's being called in the driver when you transmit the packets. So you'll see that you have some packets being sent to this this address. So this means probably it's a ping reply to this commercial device. So you are using certain modulation coding scheme. You can maximum retry 6 times, and the packet needs acknowledgement. So it's being sent from which priority queue, so on and so forth. So I can also enable some printing on the receiver side. In that case, I'll place it here. And then I will print again the kernel mode. You see now, you not only get print from Open Wi-Fi TX, but you also see the Open Wi-Fi RX interrupt. So this is a function that basically interrupt service routine that's being called when you receive the packets. So you see certain modulation coding scheme again being used, the packet length, the signal strength you have received the packet with, again the addresses, also whether it has passed the checksum. So in this case, the FCS is 1, means that it's a valid packet. But for instance, in this case, in this packet, the decoding has failed, so the FCS did not pass. So it won't be acknowledged. So I think this is about what I want to show for the demo part. Let me go back to the presentation and see if I'm yeah. Okay, so I just have one more slides after the demo. So because it's in the testbed, so we have different boards, and also sometimes different experimenters have different needs. So what happens is that we have set up some, oh, I'm sorry. It's actually here. So let me try to open it again. So I have on the top of this Openwifi tutorial, you have a hardware information page. So in this information page, you will have an overview of how each board is being connected to which node, and also how its antenna ports are configured. So for instance, for this board, we have RX1 and 2 antenna in different bands. For this board, we have actually the different types of antenna. So the RX1 port is dual band, while the other one is dual band but directional. So this one is omnidirectional, and it's pointing towards certain SDR devices. Also, because the analog device front-end board does not have a power amplifier, so sometimes in the testbed, if you want to reach another node that's further placed further apart, then you need to have a antenna connected to the antenna port connected to a external power amplifier. So we have installed, actually in this slide I show it. So we have installed a external power amplifier board that's to just boost the power. So these are all the information that you can find on this web page. So it's important, if something doesn't work or before you connect to some board, you take a look at this web page to know that which antenna port you need or which nodes you need to be reserving, because sometimes for the directional antenna, you can only form a link between certain devices. It's also very important that you match the configuration files. So basically the hardware bitstream in FPGA, the driver, and also all the Linux kernel and kernel modules. So this has to match. It's also for this reason I have provided everything like in the zipped folder precompiled. So in the future, when you use the Openwifi, you might have the need to, of course, to use different driver or hardware versions. So in that case, we have in this advanced topics, let me just try to scroll down. No, I'm in the wrong part. Okay, so in this part, you have some more specific topics. So for instance, for updating driver, kernel, FPGA, you can follow these parts to update the parts you need to update. It can also happen that some users has messed up the file system on SD card. So for that reason, we have provided this part. Basically, you need to boot the Linux through a RAM disk and then flash the entire SD card with an Openwifi image. So this is also first thing if there's any issue. So of course the command will take a while. So I think I'm at the end of the tutorial. I don't know if there's any questions.
Yes, Wei, there is well, actually 2 questions. So the first one is, in the whole hardware prototype, the analog devices front-end with the Xilinx ZC706 available as an evaluation board from you?
From me. No,
yeah,
this
that's
is
a question.
So if the question means do we make the boards? So we don't make the boards, we buy the boards from Xilinx. So we buy the boards from Xilinx and analog devices. We don't make the boards, but there is something under discussion. In the future, we might make some more compact, customized USB-based dongle-like ported boards. But this is a really long-term vision. It's ongoing. But we have such kind of ideas.
But we make them available through the testbed, so they are remotely available, of course.
Yes. So if you create an account like Black has shown in the first part of the tutorial and make reservation, then you can use the board. This is provided in the testbed. But yeah, if the question means do we provide the board in the testbed, the answer is yes. But if it means do we make the boards ourselves, then no.
Yeah, thanks. And the second question is, what about the SDR takes time slicing feature? Most vendors employ an Ethernet packet level scheduler. Where does this Openwifi time slot scheduler take place?
Time slice scheduler. Actually, for that, we also have a part of the tutorial goes to that. Let me just show you quickly. So we have a customized feature. I think it's rather customized because it allows you to define the timeshare, basically error time that a queue, or you can assign a destination address or filters. So it basically allows you to configure the transmission time of Openwifi based on certain criteria in the driver. So you can open the, I don't know where it is anymore, but okay. If you open this file, you will see there's a piece of code. If you search Dual ID here, you will find a piece of code. That piece of code basically tells you that you can implement certain sort of rules for the driver to implement, to start transmission or start transmission at certain intervals in the timer that you can configure. So this is for me, this is timeshare, time slicing. So it's basically what I want to say is this feature is configurable, and you can configure through the driver and also through the user space tools. Yep. So if you have interest, you can take a look at this part of the tutorial.
Yeah, thanks, Wei. So Kostas, does that answer your questions? If not, we can also open up your microphone, I think, if you want to ask more. I don't see, yeah, perfect, thanks a lot. So that's okay. I don't see any other questions for you, Wei.
Okay, then I think we are, for me, this is the end of the tutorial. In that case. Okay, so I will stop sharing. Thanks a lot for all the attention.
Yeah, so let me thank also you, Wei, for this tutorial. And so if you need any more information, we provided some links in the presentation. So Fed4FIRE.eu, I think, is the main one. So thanks a lot for being present, and hope you enjoy also the rest of EuCNC. So have a nice evening and see you soon, maybe. Thank you. Bye-bye.